Welcome back. Now that we have studied LDA and GGA approximations for the exchange correlation functional, we are going to move up the Jacob's ladder of exchange correlation functionals that we will see in the next slide. And we are going to explore in this screencast the advanced description of the exchange correlation functionals. We are going to focus mostly on two types of exchange correlation functionals with at least two families and with examples, and I will provide you a summary of where we go from there. I will end the screencast in the last 5 minutes talking about beyond DFT, really, talking about LDA plus U, maybe, which is still DFT, and also a little bit about GW. Thank you. So remember that this is the only piece we don't know in DFT, the exchange correlation part, which is small in value, but extremely important to describe the quantum mechanical effect. The simplest approximation is using the um, homogeneous electron gas, and it's the LDA approximation, which was surprisingly good, if you remember, because of the cancellation of errors. Next, we look at the general gradient approximation, which is not part of the Taylor series from LDA, as I mentioned, but instead it's a general function that includes the gradient of the density in different forms. So by definition, it's semi-local because it takes into account the density at a given point, but also how that density changes. Now, we have more functionals. We have the Meta-GGA, which is GGA on which we add a contribution of the kinetic energy of the cone charm orbitals. That's what the last term with the sum is about. And then beyond that rung, we have uh, hyper GGA and hybrid GGA. I'm not going to talk too much about hyper GGA, but the hybrid GGA is something that I'm going to talk quite a bit about. And hybrid GGA is pretty much the standard exchange correlation functional, which comes with a caveat, which is a higher computational cost. So I'm going to spend this screencast talking about the hybrid GGA and the meta GGA, as well as other corrections or other approaches which are really beyond functionals. So let's start with the hybrid GGA. The hybrid functionals, I already alluded to them a few times. Hybrid functions almost look like we are going backward. I mean, let me explain what I mean by that. In Hohenberg-Kohn said that all you need is the density. You don't have to worry about the wave function. But at the same time, we realize that a big chunk of what is missing in the exchange correlation functional is the exchange part. And the exchange part is related to the Pauli principle, which for fermion, so Pauli exclusion principle, for fermion means that if you have the many-body wave function, exchanging two identical particles will lead to a change in the wave function. Now, of course, we understand the conundrum now because we are working with densities. How can we impose that swapping or exchanging two electrons will lead to a change in the sign of the wave function? We do not have access to the wave function from the density directly. So this is what I mean by going backwards, is that we have to go back to trying to build some kind of many-body wave function, if you will, that's going to correspond to that density. And of course, we have the tools to do that. And the tool we have to do that is that we can go back to Hartree-Fock. And Hartree-Fock was using a Slater determinant, which of the independent particle, so of the orbitals of the independent systems, to get exact exchange, right? When we talk about exact exchange, we're really talking about Hartree-Fock. So how do we do this? Well, the way it's done is done using the cone-charm orbitals. And it's something that started in the early 90s, but really hybrid functional only became really popular later because of the computational cost. And everything can be described in the box here, the blue box. Essentially, we remember that we have to solve cone-charm equation where, of course, all the difficulties are hidden in the effective potential. VF, which include the exchange correlation potential and all that good things. Now, what the idea of a hybrid functional is that we can use those orbital, right, the psi, to build a Slater determinant. Now, if we build a Slater determinant, we obtain a many-body wave function, if you will, from the cone-charm orbitals. And that many-body wave function, by construction, because it's a determinant, if I swap two rows or two columns, I change the sign of the determinant, which is exactly what exact exchange is. So that's the idea. Now, the big difference with Hartree-Fock, of course, is that the orbitals we are using here are the cone-charm orbitals. In Hartree-Fock, we were using the solution of the independent electrons, basically. Here, it's an independent electron, of course, but the effective potential is the cone-charm potential. So that's different. But anyway, in any case, this way we can ensure that we take into account the exchange correctly. So the improvements we have when we do this is that we now get the correct asymptotic behavior for the exchange potential, since of course it obeys the exchange potential. We address a major drawback of LDA and GGA, which is the self-interaction problem. The fact that basically the exchange correlation hole, if you will, so the reduction of density around a given electrons because of its presence there. So this is an improvement in hybrid functionals. And similarly, along those same lines, we also improve the delocalization and localization. So LDA and GGA suffers from issues with localization and delocalization, and while the hybrid functional is going to be able to take into account better this localization and delocalization. And by doing that, there are many properties that are going to be captured better, like a band gap, like the reaction barriers and the geometries and so on and so forth. So clearly hybrid functionals are really an improvement over LDA and GGA. And all this is related to the better handling of the exchange correlation hole because of course the exchange piece is stronger. So that's very good. We improve a number of properties, again, not just the band gap and barriers and so on, but also the bond length, the bond angle, and the vibrational frequencies. So hybrid functionals is basically the functional that's going to be used if you want to study at small molecules or even big molecules. It's always going to be hybrid functionals if you do DFT. I mean, quantum chemists will use, I would probably say 99.9% of the cases will use hybrid functionals. So the hybrid functionals are really built on GGA. They use GGA and you build on that. And I already mentioned in the last screencast that there are different types of GGAs with different parameterization, different effect, built with using different philosophy. For example, the fit on databases like quantum chemists would do on BLIP, or the obeying a number of constraints from quantum mechanics, like the functionals like PBE, for example, or PW91, that kind of functionals. So clearly, because hybrid functionals are built on GGA, there will also be different flavors of hybrid functionals. So typically the way it's done, it's using this equation. The hybrid functional, the hybrid exchange correlation functional will be obtained by using the GGA solution and by correcting the exchange representation that's in GGA by adding a certain amount of exact exchange. And you need to do that because you want to take into account the fact, of course, that your electrons are not independent, clearly. So for molecules, it turns out that the value that's typically used is about 1/4. So you get about 25% of the exact exchange and the rest from the GEG exchange. So we end up with a better description of the exchange correlation holes, and we can also calculate the energy. If you remember, we did this when we did Hartree-Fock, the energy contribution that comes from the fact that we impose the wave function to the many-body wave function to be anti-symmetric upon exchange, lead to an energy value like this. remember I mentioned this a few screencasts ago, and that's essentially an integral that does not have a classical correspondence in classical electrostatics. This is the purely quantum mechanical effect. That energy there in that integral, and I invite you to go back to the screencast where we actually derived it. But the point is that you do have energy contribution, I mean, a contribution to the total energy from the fact that you impose the wave function to be antisymmetric. There are different types of ways. So this is the simplest way to add some exact exchange over the exchange correlation functional. There exists also some class of hybrid functionals where you have a range separation. In that case, you can, in fact, uh, add more or less exchange piece, exact exchange, depending on how far you are from the nucleus. And that allows you to really capture the different phenomena, like for example, the asymptotic behavior, the interaction with nuclei, and things like that. And if anything, these range separated hybrids, they use more parameters, therefore they're expected to be more accurate. So you can see this. These all those functionals are very effective, uh, but we are moving towards more and more cases where we have more and more adjustable parameters. And so people who want to do true ab initio start to raise their eyebrows, of course, because if you want to do ab initio, so from the first principle of nature, if you start to introduce too many parameters, you are getting into a territory where you start to be semi-empirical. Um, Now, on the good side of this conversation, um, all those parameters are actually not just moved randomly. They are changed and they are determined based on physical quantities. So this is not all bad, but we always have to be careful not to overfit and have too many parameters, because we want to make sure that we stay as close as possible to the fundamental principles of quantum mechanics. So this is the functional. This is the typical equation we use to add some exchange. There are studies. There are many studies where people look at a given material with changing the value of A. That's definitely exists. You can do that and see, and then compare these two experiments. So right now, hybrid functionals are among the most accurate functionals that you can find certainly in quantum chemistry. Um, they do not introduce really new physics in the sense that we do not obey more exact constraints, for example, in those functional like the one I'm going to describe now. So one is the by far the most popular one in chemistry, and when I say by far, I really mean it. It's really overwhelmingly popular. It's called the B3-lip. So B is for Becky, which already saw. Lip, Li, Yang, and Par. We discussed B-lip. B-lip was the GGA. B3-lip is actually hybrid functional. And the number 3 means that there are 3 parameters in the description for the B-lip. So these have been found to work extremely well for bond length and many properties like ionization energy, formation energies in molecules. So it's very, very popular. And just as we have discussed before, the other train of thought, if you will, is to, instead of using a database of a large database and a diverse database of molecules to find the parameters, you can also focus on obeying the constraints, and this is more like the kind of the Purdue school of thought for exchange correlation functionals. And so the hybrid functionals that correspond to PBE that we discuss at length is the PBE zero, and that functional is actually used in solid state physics. The problem with PBE zero is that it's computationally quite expensive and it's a significant. It takes significantly more time to do a PBE zero calculation than a PBE. On top of that, the scaling, so the speed, the evolution of the speed as a function of the number of electrons is actually much worse. So the scaling is much worse for PBE0. We are going to discuss that more. Another example of popular hybrid function is HSC, which is from Haid, Skuzeria, and Erzenhoff. So Erzenhoff, the same person from the same E from PBE. That one use a little a different way to deal with the screen column potential, and it's actually very computationally efficient. So HSC is typically more efficient than PBE0. So you will see a lot of papers in the literature where people do hybrid functionals for solid and surfaces. People would use HSC. So that's good. And this is a slide I already showed you in the previous screencast, and I asked you to focus on the blue line. Now we can look at the green line, and the green line shows how the band gap, the calculated band gap we're using an hybrid functional like HSC compares to the experimental band gap. As always, a perfect match between theory and experiment would go on the bisector, on the dashed line. Instead, here, it don't quite go on the dashed line, but clearly the HSC functional is much closer to 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 the experimental data than GGA, which always underestimate the band gap. I mean, most often underestimate the band gap. Um, so that's good news. And you can also say all those bunch of points which are close to zero. Some of them actually calculate the GGA band gap would be negative, which is essentially a metal, while at least HSC gets it right. So HSC is really, really useful. So many people are studying systematically how good those functionals are, like HSC again. And you can see here on this plot from a fairly recent paper that, as you know, GGA always underestimate the band gap, and in this case, HSC systematically correct for that in terms of the band gap correction, make it closer to reality. So that's what you get from the hybrid functionals. I am not including here an example of B-tree-lip. It's not that examples are lacking. There are many examples, but we are going to see a little bit more data about benchmarking between different functionals in just a few minutes. So another functional that's used, and I'm sorry, we are going essentially backward in terms of the rung, is go back to the rung 3. So we are moving down from a hybrid functional like the rung 4, and we are moving back to rung 3. And in that case, why do we do that? Well, we do that because we are kind of a conundrum, especially for large system and solid state system, where GBA is not bad at all, but it suffers from a number of issues like band gap, like self-interaction error. It's not bad for structures, for example, not bad for electronic properties, but it's not. It could be improved. We would love to be able to do hybrid functionals on everything. The problem with hybrid functionals now is that the computational cost is just high. It's actually very high. So as always, when you have something that works pretty well but not great, and you have something that works very well but it's slow, you try to find a compromise. And the compromise is actually provided by Meta-GGA, is the rung 3 in this ladder introduced by Purdue. And that functional is also a semi-functional. So I'm talking about the R3 there, the exchange correlation Meta-GGA. And that functional includes the kinetic energy of the Kohn-Sham orbitals. That's what the last part of between parentheses is related. This is still a semi-local functional as opposed to the hybrid functionals which are fully non-local. So let's talk a little bit about Meta-GGA because I think it's useful. So this is just as I told you now. We include the kinetic energy of the Kohn-Sham orbitals. So this is a good because the Meta-GGA, because you have an additional ingredient, allows you to improve upon GGA without having to pay the cost of hybrid functionals. So that's nice. Now, there are a number of key features. Is because of the introduction of the kinetic energy density, you get a little bit more a better treatment of electron localization, which is actually nice because electron localization is one of the shortcomings of GGA or even maybe worse, LDA. So Meta-GGA as a result is more accurate. You really improve pretty much all the properties compared to GGA, barriers, bond lengths, atomization energies. Not quite as good as hybrid functionals, but at a much lower cost. That's what is nice about it. So I know I'm giving a lot of information about comparing the different exchange correlation functionals. I put together one slide summarizing how they are doing in different areas. So do not worry too much. Think about Meta-GGA, I mean, yet, just yet, but think about Meta-GGA as being something with accuracy that's somewhere between GGA and a hybrid functional without the sometimes prohibitive computational cost of hybrid functionals. So there are a number of Meta-GGA functionals. Do not pretend that I'm going to make a full list. It's just not possible, and people keep developing them. But some of them are pretty well known. I mean, one of the first one was the TPSS from Tao, Purdue, Staroverov, and Skuseria. So demonstrating actually one of the nice things with TPSS is that it demonstrated that you improve upon GGA without a crazy cost. One Meta-GGA that's fairly popular right now is the scan functional, and you will notice that in this case, SCAN do not stand for first letters of the authors, but instead means strongly constrained and appropriate norm functional. So this one actually works pretty well. And what is nice about the scan functional is that it's very transferable because it has been developed for using strong constraints, a lot of constraints from quantum mechanics instead of fitting. I should also mention some Meta-GGA more into the chemistry realm, like M06L, which is from the Trulars group. It's also very accurate in more into the chemical arena. So let me tell you a little bit more about scan. But before I tell a bit more of scan, I just want to summarize that Meta-GGA is a good balance between computational cost and accuracy. So that's what makes it very attractive. But let me tell you a little bit more about one particular functional, the scan functional, which has the strength, really the strength of scan is that he actually obeys 17 exact constraints. So the goal being that if you keep satisfying the constraints, you should be able to get closer and closer to the right, to the exact exchange correlation functionals. Just as a spoiler alert, we still don't have, nobody still knows the exact exchange correlation functional at this level. But I gave you a number of constraints when I talk about GGA, the development of PBE. So here we can actually add even more constraints. It's becoming very technical, so I'm not going to tell you what they are. But of course, you can easily find that information as a further reading from this course. So it's very versatile across systems since it's built on fundamental principle, which is nice. It can do very well in all sorts of systems like molecules, solid metals, layered materials, even not too bad with van der Waals. It's not the perfect with van der Waals, but at least he start to capture some of it. And as I'm going to show you an example where you can actually use some kind of hybrid. I should not use the word hybrid because it's not a hybrid functional, but some kind of functional that's built between van der Waals functional and scan that gives extremely accurate results, not just for van der Waals, but also for all the other good properties that scan can do. It's very good for weakly bonded system as opposed to GGA, which is because of its semi-locality, is not that great in that case. And as I said, the computational efficiency, sure, scan is more computational expensive than GGA, for instance, but it's not prohibitive compared to hybrid functionals, especially for large systems. So scan is great. It's still not the panacea. I mean, no exchange correlation functional is the panacea. It still sometimes overestimate the lattice constant. is not doing that great with strongly correlated electron system, like most exchange correlation functional have problem with that. But it's a very useful functional. So here are some benchmark that come from the original paper on scan. These are three different kind of clusters, molecules there, where just for the sake of time, let's just look at the first one on the left-hand side, and then we compare LDA, PBE, scan at HSC. So from black, red, green, and blue, it's basically climbing the ladder, the Jacob's ladder, and we want to reach the accuracy of experiment, of course. The experiment is the true accuracy, is your standard. LDA is not doing too bad, but not great. PBE improves upon LDA. HSC, hybrid functionals, is doing pretty good in blue, but we see that scan is also reaching accuracy that's very close to experiment. And this is true for the three different types of systems. So again, why wouldn't you use hybrid functionals for everything? Well, because of the computational cost. So as I mentioned to you, scan can also encapsulate some of the van der Waals interaction. This is a busy plot, so let's just focus on the argon dimer. We can the reference is in black. It's the bottom curve that's behind the red and purple ones. The one of the curves with the red triangles is a van der Waals functional RVV10, doing pretty well. It's done on purpose. I mean, it's been designed for that. Scan is doing okay. I mean, this is the blue line. It's either shift, but it finds the same minimum distance. But you can actually modify scan to put some of the van der Waals corrections from RVV10, and then you end up with those purple losanges, which are very close to experiment. But on top of that, you could say, well, why not use RVV10 then? Well, because if you use scan plus RVV10, you also have all the good representation of all the other physical properties from Meta-GGA. So you see, you can start it start to become an art here when you look at those kind of system. And my goal in this screencast is really to make you aware that there are so many functionals out there, and it's worth it to look into this these descriptions when you start a project. It's not so much about learning them by heart or anything like this. I mean, you will know them just by using them. And some of them you will never use, and so you will not remember them, and that's okay. But at least be aware of these different classes of functionals. And most importantly, do make sure when you reach a conclusion, when you write a paper or a report, make sure that you do not overreach. As I already mentioned, do not overreach. Be mindful of this error bar that's inherent to those different functionals. I mean, for example, you're going to calculate a band gap with LDA or GGA, and you know that band gap is going to be grossly underestimated. It's still a valid result. I mean, you have to be aware that yes, the band gap is, you can look at trends and evolution of band gaps. You just can't reach a conclusion that if you find a band gap, let's say of 3 eV, and the experimental band gap is 3 eV, if you do that with GGA, clearly you have to think a little bit harder, because GGA should not be able to reproduce the experimental band gap. Okay, so here is another example. I mean, there are plenty of benchmark everywhere that we can look at. This is another interesting plot where we compare LDA, PBE, the Meta-GGA, in this case TPSS, the first one I mentioned, and then a hybrid functional. The hybrid functional does better, but TPSS also does better than PBE and LDA. So this is really about systematic improvement. And people have looked at large table like this. Of course, I'm not expecting you to read the table, but you can look at the different values. How, for example, let's pick, I don't know, let's pick boron nitride, the not the last row, but the one before last, and look at the lattice constant. We see the lattice constant for PB for experiment is 3.6, and LDA is actually pretty good, right? And overbind, as you know, that means that it's smaller, right? It binds too much. TBE, as I told you, will overbinds a little bit, so underbinds a little bit, so the lattice constant is a bit longer. TPSS actually does not improve that much in terms of lattice constant, and HSE is going to get you a bit closer to the experimental value. And in terms of band gap, though, hybrid functionals will be a significant improvement compared to all the local like LDA or semi-local like PBE and TPSS. So these are all things that maybe if you want to look more, I invite you to pause the screencast and to look into that. Now, computational cost of the different methods. I like to discuss this a little bit. The only methods that are DFT are the first two rows. In fact, I mean, strictly speaking, only the first one. And one of the attractiveness of DFT, of course, is that it's an n-cube. It's an n-cube. It has an n-cube scaling law, where n is the number of electrons in your system. The second row is still DFT, but it's using hybrid, so it's using Hartree-Fock exchange from the Kohn-Sham orbitals, as I explained earlier in this screencast. And all the other rows are starting to be really, really computationally demanding. And all those, like MP2, MP3, MP4, and so on, these are Moller-Plesset perturbation theory on Hartree-Fock. They are very accurate, but they're used for molecules mostly. But the scaling law is really strong. Just for your information, CISD will be configuration interaction single determinant, CCSD couple cluster single determinant, and so on and so forth. So these are really all those methods are, aside from the first two rows, all those methods are actually quantum chemistry methods built on top of Hartree-Fock, really. They are not DFT methods, but it's also always useful to remember why DFT is so popular, is because it's computationally much more feasible than those methods. So I put together the following tables. This is maybe a table that's the most useful for this entire screencast for you. And this table, I compare the four types of functionals that we looked at in this course. So the local, semi-local, and non-local. Try to summarize this. On the last row, you have some examples of the functionals. I think that encapsulate most of them. And then you see the table itself about the quality of the structure, the energy barrier, the band gap. You can see, I mean, I'm not going to read in detail this slide, but if you could do hybrid, you would do hybrid. I mean, this is by far the most accurate. There is just a little issue is that it scales as N4 and it's the slowest technique. But a good compromise may be the Meta-GGA. Meta-GGA is pretty good with structure, pretty good with energy barrier, improved with band gap. I mean, if you make a 40% error, can you say it's pretty good? I don't know. It's still pretty high underestimation. So be aware of that. But in reality, if you look at the literature, many people actually use GGA and even sometimes LDA. Sometimes LDA is enough. We see fewer and fewer papers using LDA, but that's, that's the advantage of LDA is that we understand well the shortcomings because there's not many free parameters in LDA. So that makes it a little bit easier to understand what you have. Now, on top of those functionals, of course, there are more developments going on, and development in the exchange correlation functionals are pretty much constant. And then, of course, with the advent of machine learning, there are a number of people are using machine learning to get to build functionals. Even B3Lib to some extent is really based on machine learning, right? Because it's a fitting parameters, and when you do a deep networks, very often those deep networks are mostly about fitting numbers. But there are also some neural network-based exchange relation potential model or even global descriptors. They usually do pretty well. It's still very much under development. I think by the time I will upload this video on YouTube, there will be probably more papers published in just a few minutes before now and the time I upload this video. I'm not going to go too much into the details of this. But there is this paper that I find very interesting that I was reading as I was preparing this presentation, which is a review paper from 2023, so fairly recent, that provides a nice overview of where we stand. We exchange correlation functional developed from machine learning. Of course, the machine learning issue is always the same, right? I mean, you can get very good result for systems and structures that are within the realm of of the training set. So you do not want to end up in a situation where you develop an exchange correlation functional which is very accurate for a class of system. Remember, the key ingredient we want for an exchange correlation functional is to be universal. So that's why training over a very large basis, a large set like blib or b3lib do, or even better, in my opinion, in my biased opinion, even better using the constraint, the fundamental constraint from quantum mechanics, uh, ensures that you have more universality. So you always have to do this with care. Be careful about that. Now, I'm going to finish this screencast in a few minutes by telling you that there are more things that are done on top of DFT and exchange correlation to improve things a little bit better in terms of representing the physics that you see experimentally. So those corrections are of three types, essentially. There are strong correlations effect, quasi-particles. So this is mostly for optical properties, and van der Waals. So as I promised, the van der Waals piece, which is how you improve the van der Waals description, is going to be the subject of the last screencast of this course in terms of the tutorial of the fundamental knowledge. So I'm just listing it here, but I'm not going to talk about this in the screencast. I'm going to talk very briefly about the first two. The first one is strong correlation, which is something that I already mentioned when I spoke about LDA. And LDA, one of the problems with LDA is this localization. And LDA doesn't do very well with localized electrons. And those can be found when on those elements that have D or partially occupied D and F orbitals, because they are more localized, as I showed you a picture of that a few screencasts ago. So the U term essentially add this on-site repulsion, if you will, and it makes sure that the localization is better taken into account. That allows to shift the orbitals with respect to one another, and basically correcting from this for these shortcomings of LDA. So LDA plus U is used very much into those more correlated system, also a lot in magnetic systems as well, which are sometimes when the magnetism comes from the D and F orbitals in particular. So U will be a fitting parameters. Again, we are kind of stepping away from this first principle idea, but this is something we do to understand what's going on. And very often you will see people writing papers using these techniques, but usually hand in hand with experiment, because the idea would be to try to understand how can we establish this handshake between experiment and theory. So LDA plus U would be your typical case of opening gaps in insulator. So LDA, the band gap is not that great. We are missing out quite a bit, as we discussed in a specific screencast. Using U can be helpful. So there are many examples out there. I mean, when I prepared these slides, I found this example, and I think it's useful because it also shows us how we can compare different methods. Um, so look at the top right, the top left plot where the band gap is compared between experiment and different techniques. As I mentioned earlier in this screencast, HSE, so the hybrid functional, is doing pretty good job with the star point. It's doing pretty good job with experiment. The problem is that we can't use HSE for larger system or heterostructures or system like this. So you can use LDA, or in fact GGA, because I mentioned you can use a U term on LDA, but you can use a U term on GGA as well. You would be probably seen the word LDA plus U more than you would see the word GGA plus U, but there's no, the people are also using GGA plus U. And what you see on the two curves, still on the plot on the top left, is that when there is no U term, so for U equals 0, the band gap for LDA GGA is equally poor, and underestimated here more than 50%. And it's particularly true for this strongly correlated system. However, if you change the U parameter, you calculate a band gap that increases as expected because you are doing those repulsion term, and you end up with a value that can actually match experiment, which is actually pretty large in this case. A U of 12.5 eV is actually a fairly large number. And then you can compare the effect on the Cohen-Sham orbitals. That would be the four plots on the right-hand side of this plot. And you can see that when you increase U, the different bands are moving depending on what bands they are, if they're s orbitals or if they're d orbitals, and you see the effect on the d orbital. Now, if you look at this, if you compare C and D, the band gap between C and D, so between hybrid functional HSE06 and LDA plus U with a large U of 12.5, see the band gap is similar. Unfortunately, the ordering of the bands is not correct. So you have to be careful about using those parameters, because when you do that, you get something that looks good, but when you analyze in detail, you realize that the band gap you see in LDA plus U, for example, in this case, is actually correct. The band gap is correct, but it's not the right transition. It's not the transition between the right orbital. So you have to be careful about that. Now, talking about band gap, you have the transport band gap, which is typically the band gap between the HOMO and LUMO, but you also have the optical band gap, which is the gap that you see from optical measurement. And clearly, if you excite an electron, so you take an electron and you move it from the conduction bands to from the valence band to the conduction bands, you are going to create an electron-hole pair. And in a nutshell, this is not a course on quasi-particles, but in a nutshell, this electron-hole pair is going to create like a particle, like a quasi-particle. In fact, it looks very much like a hydrogen atom, right? You have a hole, which is like a proton, and you have an electron. And so there is an interaction between them, an attraction between them. And in fact, there are models that show that you can use hydrogen-like theory to explain this phenomena of exciting an electron and leaving a hole behind. The right approach to do it is it's called there are different methods to do it. I mean, like Beth-Salpeter approach or GW. I'm just going to mention GW. GW method was introduced about 60 years ago by Hedin. And the idea there is to really look at look at the fundamental phenomena of the excitation of the electron and interaction with the hole. And so that's why it's usually called quasi-particle, because electron hole generates a quasi-particle. And of course, because of this this notion of binding energy, the fact that the electron and the hole interact and are attractive to each other, makes the optical band gap lower than the transport band gap. And I hope it's clear. This is not a screencast on GW, just give you an idea. But why am I talking about GW on your DFT course? Because GW is not DFT. I mean, that sometimes it's also something we hear. Oh, GW is correct, is like an exchange correlation function in DFT. It's not. It's not at all. GW is a perturbation theory. It is, as you know, DFT is a ground state theory, so we can certainly, even fundamentally, not hope to be able to represent it. However, everything is the word perturbation. A perturbation theory, you need to start from somewhere in order to do the perturbation. So the idea of heading there, the GW, is a perturbation on something you know, and it turns out that the DFT result is a very good starting point for GW. It basically gives you the non-perturb approach over which you apply the GW perturbation. So you could actually write a full course on GW, which I am not doing, but it's basically the idea when you have many DFT courses that DFT codes that actually include a GW module. It's not but it's not DFT. It's just that it's using the DFT result to build the quasi-particles. I hope that's clear. Here on this slide, I'm showing two things. The first one is that the band gap in GW is really good, and the physics is also well encapsulated and certainly improved with LD compared to LDA. So that's really nice. These are just some examples. So you can find many examples where GW gives you almost the exact band gap. And you see, interestingly enough, if you look at the legend of this plot, uh, the cyan, the circle in cyan, the legend is GW, and with LDA in parentheses, basically says that GW is a perturbation over the LDA result. I think there are many studies that have shown that where you start from of GGA or LDA doesn't make a huge difference in your GW band gap. Again, beyond the scope of this. The other thing I want to show you is that if you're excited about GW, there are a lot of resources online, or even in papers, in books. I find the one from Paolo Umar quite interesting. So I actually provided a QR code to their PDF file. It's actually a short presentation, but it's very illuminating and explain basically how it works. So if you don't find any others, you can use that one. I recommend this one, but there are plenty of possibilities. So thank you very much. It was a very much packed screencast. Um, I hope you followed everything I said. And at the end of the day, what really matters for you is to maybe keep in mind the table, the summary table I gave you about the different advantages of LDA, GGA, Meta-GGA, and um, and uh, and hybrid functionals. Take into account the fact that we can also have additional corrections like LDA plus U, or go completely into perturbation theory like GW. Thank you very much for your attention, and I hope to see you for the next screencast. Thank you.